Welcome to today's paper reading. Today's paper is titled, The Boundary of Neural Network Trainability is Fractal. This paper was published on the AR14 preprint by Jascha Sohl-Dickstein. In this study, we explore the fractal nature of the boundaries between neural network hyperparameters that result in stable versus divergent training. This investigation is inspired by the fractal boundaries observed in mathematical sets like the Mandelbrot and quadratic Julia sets, which are determined through the iteration of functions and the identification of divergence or boundedness. Similarly, neural network training involves the iterative process of gradient descent, which can exhibit convergent or divergent behaviors and is highly sensitive to small changes in hyperparameters. Our experiments reveal that these boundaries are fractal across more than 10 decades of scale, regardless of the network configuration tested. In fractal generation, a fixed function is iterated repeatedly, and the set of points where small changes to hyperparameters lead to dramatic changes in the sequence of iterated values is kept. These points define a boundary in hyperparameter space where dynamics bifurcate. For neural network training, gradient descent steps are iterated, and hyperparameters can lead to bifurcation boundaries between converging or diverging training runs. The final loss value achieved during training has been shown to have a chaotic dependence on hyperparameters. This paper aims to visualize the bifurcation boundary between hyperparameters that lead to successful and unsuccessful training of neural networks across various experimental conditions. In this section, the experiments focus on training a one-hidden layer neural network with inputs x is an element of Rn and parameters w0 is an element of Rn times n. W1 is an element of R1 times n. The network is trained on an MSE loss function, with weights, data points, and labels all initialized randomly from a standard normal distribution. The training process involves 500 to 1000 iterations of full batch steepest gradient descent, with a 2D grid search conducted over learning rates A to 0 and A to 1. Visualization of the training results shows divergence in shades of red and convergence in shades of blue, with color intensity proportional to the loss. The boundary between trainable and untrainable hyperparameters exhibits fractal characteristics. Figure 1 illustrates the fractal nature of the boundary between trainable and untrainable neural network hyperparameters across various experimental conditions. The figure presents a 2D grid search over neural network hyperparameters, with red points indicating training divergence and blue points indicating training convergence. Paler colors correspond to faster convergence or divergence. The experimental conditions include different network nonlinearities, both mini-batch and full-batch training, and grid searches over either training or initialization hyperparameters. Each image is linked to an animation that zooms into the corresponding fractal landscape, revealing the depth at which float 64 discretization artifacts appear. The experimental code, images, and videos are available at the provided GitHub link. In high-dimensional spaces, neural network training involves iterating complex functions, resulting in fractals that appear more organic with less symmetry. This contrasts with simpler fractals defined by low-degree polynomials. The non-homogeneity of the boundary in hyperparameter space suggests that properties vary significantly across different regions, with some regions not exhibiting fractal behavior. Stochastic training, due to mini-batch sampling, also generates fractals, indicating a connection to Lyapunov fractals where the iterated function changes at every time step. In this section, the author expresses gratitude to Mars Miyakawa and Sohl-Dickstein for their contributions. Specifically, they acknowledge the inspiration provided by Sohl-Dickstein for the original idea behind the research. Additionally, the author thanks them for their detailed feedback on the fractals generated during the study. This feedback was crucial for refining the research outcomes and ensuring the quality of the results. Thank you for watching.